Let's take a look at some table operations in execution plans in SQL Developer. I have a simple query here that you might have in an application if you are searching for a particular applicant, in this case by their zip code and by their last name. And currently, there are not any indexes on the applications table. So I'm going to execute an auto trace on this statement and let's see what we get. So we see we are indeed getting a table scan full operation. A couple of things that we notice is that we are indeed reading a large number of blocks, in this case over 1700. This is what we expect because we do have a full table scan operation, and of course we know Oracle has to read through all the blocks for the table. We also see that this query has a relatively high cost, which again is something that we expect based on the fact that Oracle's having to do a sequential scan through all the data to find the rows of interest. If we scroll out to the right and look at the filter predicates, we see the conditions of our where clause are listed as filter predicates, which, as we know, means that Oracle's first reading all of the rows and then it's applying this as a filter. Finally, looking at the last output rows column, we see there's exactly one row that's being matched in our where clause, and that's being returned by this operation. So all the data here is what we expect on a full table scan operation. Oracle has to sequentially scan through all the rows in order to apply the filter it needs to, and the result of this is a high number of logical I/O operations and ultimately a high cost. This situation is not just limited to select statements. Let's perform an update statement with this same where clause and we'll observe the same behavior. And here again, we see we have a high number of consistent gets or logical reads, a high cost for the operation, and again, Oracle lists our where clause as the filter predicate if we scroll out here to the right. So no surprises here. It doesn't matter if you're querying data using a select or performing an update or delete statement. The problem that faces Oracle is the same. It has to scan through all of the data in the table in order to find the rows of interest, and for a table of any size, this is going to be an expensive and inefficient process. What I want to do now is I first want to roll back from our update statement to make sure that we didn't impact any data, so I'll go ahead and do that. And now I'm going to create an index on the applications table on the zip code. So let's go ahead and do this. Okay, and now we have an index, and we'll be able to demonstrate a table accessed by row ID by running this same query up here. So once again, I'm going to run an auto trace on this query, and we'll see what we get. So as we would expect, we see Oracle using the index that we just created. What is happening is that Oracle is using the index operation to get back all of the row IDs of the rows that have this zip code 11201 that's specified in our where clause. And if we look at the last output rows column for our index operation, we can see that this operation returned 29 rows that have this zip code of 11201. In the next segment, we'll talk more about index operations, but what comes back from this index operation is not the rows themselves, but the row IDs. These are the values that point to the locations of the rows in the table. And this is where our next operation, the table accessed by index row ID, comes in. This is where Oracle is taking those row IDs and looking up first each block that contains the data and then the exact row inside of the block, and that's what's occurring in this step right here. We see that the table accessed by index row ID lists 31 logical IOs, but remember, this is inclusive of the subtree, and therefore the 2 IOs that were performed on the index. So there are really 29 blocks being read on the table. What this tells us is that those 29 rows that have the matching zip code are randomly distributed throughout our table, and so Oracle has to go read 29 different blocks. Still though, this is much more efficient than before, where we're having to read and process over 1700 blocks. Correspondingly, we see that the cost of this operation is much lower. Now we aren't done at this point. In this case, our index only told us what rows had a zip code of 11201, but we have a second condition in our where clause to fulfill, and that is to find the applicant with the last name of Rivera. To do this, we'll scroll out to the right here, and we can see that the filter predicate is being provided here on the table accessed by index row ID operation. And so this is where Oracle is applying that second condition in the where clause. So we'll scroll back to the left here, and what Oracle is doing is we're first using the index to find the rows with the matching zip code, looking up those rows in the table, and then we're applying a filter predicate to those 29 rows that had the matching zip code. And the end result is we locate the one row that is of interest to us. What you're seeing here is a typical scenario. You're not always going to have an index that matches every column in your where clause. But if Oracle can use an index, it can first trim down the data set to a small subset of rows, and then apply the filter predicate only against those rows. So overall, we see that when we're doing a lookup of just a subset of rows in a table access by row ID operation, the entire execution plan is much more efficient.